Now let's talk about edge locations and why they are such an important part of the AWS Global Infrastructure. So far, we've talked about regions and availability zones, which are mainly focused on where applications run and how we achieve fault tolerance. Edge locations serve a different purpose. They are all about performance, low latency, and security close to end users. An edge location is a small AWS data center placed in major cities around the world. There are far more edge locations than regions, which allows AWS to bring services physically closer to users, sometimes just a few milliseconds away. These locations primarily support services like Amazon CloudFront, Amazon Route 53, AWS WAF, AWS Shield, and AWS Global Accelerator. Reduced latency and better performance. One of the biggest benefits of edge locations is latency reduction. When users request content, like images, videos, or static web files, AWS can serve that content from the nearest edge location, instead of sending the request all the way to the origin server in a region. This means faster page loads, smoother video streaming, more responsive applications. With services like Amazon CloudFront, frequently accessed content is cached at edge locations, so users get results almost instantly. AWS Global Accelerator goes even further by routing traffic onto the AWS Global Backbone network at the nearest edge location, avoiding congestion on the public internet. Enhanced security at the edge. Edge locations also play a critical role in security. Services like AWS Shield and AWS WAF operate directly at edge locations. This means malicious traffic can be detected and blocked before it ever reaches your application. For example, AWS Shield protects against DDoS attacks automatically. AWS WAF filters threats like SQL injection or cross-site scripting. Bot control blocks unwanted automated traffic at the edge. This not only improves security, but also reduces load on your back-end systems. Offloading traffic from origin servers. Another key benefit is offloading traffic. By serving cache content from edge locations, fewer requests reach your origin servers. Your applications scale more easily. Back-end resources are protected from spikes in traffic. This improves reliability and can also reduce costs, since less data is transferred from the main region. To summarize, regions run your workloads. Availability zones provide high availability. Edge locations make applications faster, more secure, and more scalable. For the Cloud Practitioner exam, remember this clearly. Edge locations are about low latency, content delivery, and security close to users, not hosting compute resources. This distinction appears very often in exam questions, so it's an important concept to master. Before we talk about edge locations, it's important to clearly understand how AWS regions and availability zones relate to each other, because this relationship is fundamental to how AWS achieves high availability and fault isolation. At the highest level, we have an AWS region. A region is a large geographic area, such as North America, Europe, or Asia Pacific. Each region is completely independent from every other region. That means it has its own power, networking, and physical infrastructure, and a failure in one region does not affect another. Inside each region, AWS operates multiple availability zones, often called AZAs. An availability zone is one or more data centers located within the same region. These data centers are physically separate from each other, typically miles apart, but they are connected using high-speed private fiber networking. This design is very intentional. Because AZAs are physically separated, a problem like a power outage, flood, or hardware failure in one OS does not impact the others. At the same time, the low latency connections between OSs allow AWS services to replicate data quickly and support fast failover. Think of it this way. A region gives you geographic isolation. Availability zones give you fault tolerance and high availability within that region. AWS best practices recommend deploying applications across at least 2 availability zones. This way, if one AS becomes unavailable, traffic can automatically shift to resources running in another AS, often without users noticing any disruption. It's also important to remember an exam key point. Availability zones never span multiple regions. Each OS belongs to exactly one region, and regions never share OSs. So in summary, regions contain multiple ASs. OSs are isolated but closely connected. Using multiple OSs inside a single region is the primary way to achieve high availability on AWS. Once you understand this relationship, everything else, load balancing, failover, and disaster recovery, starts to make much more sense. Now that we understand how regions and availability zones work together, let's look at how edge locations fit into the AWS Global Infrastructure, because they play a very different role. Edge locations operate outside of regions and availability zones. Their main purpose is not to host applications, but to bring AWS services closer to end users to improve performance, security, and responsiveness. Unlike regions, which exist in specific geographic areas like North America or Europe, edge locations are globally distributed across hundreds of cities worldwide. There are far more edge locations than regions, which allows AWS to reach users almost anywhere on the planet with very low latency. Here's how the relationship works in practice. Your core resources still live in a region. For example, your application might run on EC2 in US East 1, and your data might be stored in Amazon S3 in that same region. Edge locations do not replace regions, they connect to them. When a user accesses your application, instead of their request traveling all the way to the region every time, AWS services like Amazon CloudFront route the request to the nearest edge location first. If the content is already cached there, such as images, videos, or static files, it's delivered immediately from the edge location. If the content is not cached, the edge location retrieves it from the origin in the region, stores a copy, and then serves future requests locally. This dramatically reduces latency and improves the user experience. Edge locations also act as entry points for critical AWS services. Amazon Route 53 answers DNS queries from the closest edge location. AWS WAF filters malicious traffic at the edge before it reaches your application. AWS Shield mitigates DDoS attacks as close to the source as possible. AWS Global Accelerator routes traffic onto AWS's private global network from the nearest edge location. So instead of traffic hitting your region directly over the public internet, AWS intercepts, optimizes, and secures that traffic at the edge, then forwards only clean, optimized requests to your region. To summarize this relationship, regions host your applications and data. Edge locations accelerate, protect, and optimize access to those resources. Edge locations are globally distributed, while regions are geographically limited. Edge services improve latency, security, and scalability without changing your core architecture. This design allows AWS to deliver fast, secure, and globally consistent experiences, even when your application runs in just a single region. Now let's clarify one of the most common points of confusion on the exam: the relationship between availability zones and edge locations. Even though both are part of the AWS Global Infrastructure, they serve very different purposes. First, think about availability zones. Availability zones are where your applications actually live. This is where AWS runs compute, storage, and databases, services like EC2, RDS, and DynamoDB. When you deploy an application, your servers, databases, and backend logic are placed inside one or more availability zones within a region. AWSs are designed for durability, fault tolerance, and high availability. They are physically separated data centers with independent power, networking, and cooling, but they're connected with fast, private links. Now contrast that with edge locations. Edge locations are not where your applications run. Instead, they are designed to optimize how content is delivered to users around the world. Edge locations cache content, such as images, videos, static files, and API responses, and serve that content from locations physically close to end users. This dramatically reduces latency and improves performance. So here's the key distinction you should remember for the exam. Availability zones host your application and data. Edge locations accelerate delivery and protect traffic. In other words, application logic runs in availability zones. Content delivery and request filtering happen at edge locations. Another helpful way to think about this is persistence versus speed. Availability zones provide persistent, durable infrastructure. Your data is stored there, replicated across AWSs, and protected against failures. Edge locations focus on speed and responsiveness. They don't replace AWSs, they complement them by making applications feel fast and responsive globally. How traffic and data flow together. Now let's connect everything into a single flow. 1. Your application and data are deployed across multiple availability zones within a region to ensure high availability and fault tolerance. 2. Static content and frequently accessed data from that region are cached at edge locations using Amazon CloudFront. 3. When a user makes a request, Amazon Route 53 directs them to the nearest edge location. 4. If the content is already cached, it's delivered immediately from the edge. If it's not cached, the request travels securely over AWS's optimized global network back to the region, retrieves the data, and then caches it at the edge for future requests. This layered design is extremely important to understand. Regions plus availability zones provide resilience and reliability. Edge locations provide global performance, security, and low latency. Together, they allow AWS customers to build applications that are both highly available and fast anywhere in the world. This relationship is a core concept for the Cloud Practitioner exam, and once you see it this way, the questions become much easier to answer. Now let's talk about how AWS actually achieves high availability, because this is one of the most important architectural concepts for both real-world systems and the Cloud Practitioner exam. In AWS, the most effective way to achieve high availability inside a single region is by deploying your application across multiple availability zones, also called AZs. Remember, an availability zone is an isolated data center, or group of data centers, with its own power, cooling, and networking. Even though AZs are close enough to communicate with very low latency, they are physically separated so that a failure in one does not impact the others. The core idea behind high availability is redundancy. Instead of relying on a single data center, you duplicate critical components so that if one fails, another can immediately take over, often without users noticing anything. Distributing compute across multiple AZs. Let's start with compute resources, like Amazon EC2. A common mistake is placing all EC2 instances in a single availability zone. If that OZ experiences a failure, your entire application goes down. The best practice is to spread EC2 instances across at least 2 OZs within the same region. For example, instead of launching all servers in US East 1A, you distribute them across US East 1A and US East 1B. This way, if one OZ becomes unavailable, the other continues serving traffic. When you combine this with auto-scaling, AWS can automatically detect unhealthy instances, terminate them, launch replacements in healthy OZs. This happens automatically, helping maintain availability without manual intervention. Load balancing across OZs. Next comes elastic load balancing, which is a key component of high availability. An elastic load balancer sits in front of your application and distributes incoming traffic across resources in multiple OZs. Two important concepts here. Health checks. The load balancer continuously checks whether instances are healthy. Failover. If instances in one OZ become unhealthy, traffic is automatically redirected to healthy instances in another OZ. With cross-zone load balancing, traffic is evenly distributed across all instances in all OZs, ensuring consistent performance and resilience, even during partial outages. Data redundancy with multi-OZ services. High availability isn't just about compute, it also applies to data. AWS provides many managed services that replicate data across multiple OZs by default. Amazon RDS Multi-OZ. Your database runs in one OZ, while a synchronized standby runs in another OZ. If the primary database fails, AWS automatically fails over to the standby, often within seconds, without changing the database endpoint. Amazon DynamoDB. Data is automatically replicated across 3 OZs, giving you built-in fault tolerance and high availability without manual configuration. Amazon S3. Objects are stored redundantly across multiple OZs, providing extremely high durability and availability. This means AWS handles much of the complexity for you when you use managed services. Putting it all together, a highly available architecture. A typical highly available architecture on AWS looks like this. An elastic load balancer routing traffic across multiple OZs, EC2 instances in an auto-scaling group distributed across those OZs. A multi-OZ database, or a service like DynamoDB, for resilient data storage. With this design, a single data center failure does not bring down the application. Traffic automatically shifts to healthy components. Users experience little or no downtime. For the exam, remember this rule. High availability within a region is achieved by using multiple availability zones. Regions provide geographic isolation. Availability zones provide fault tolerance and resilience. If you understand that distinction, many cloud practitioner questions become much easier to answer. Recognizing that availability zones do not share single points of failure. Now let's focus on one of the most critical architectural principles in AWS, and one that appears very often on the cloud practitioner exam. Availability zones do not share single points of failure. This idea is at the heart of AWS's approach to resilience and high availability. The design philosophy, isolation and independence. AWS designs each availability zone as an independent failure domain inside a region. That means an availability zone is not just a logical separation, it's a physically and operationally isolated environment. If something goes wrong in one OZ, AWS engineers design it so that the problem does not automatically affect any other OZ in the same region. This intentional isolation allows customers to build fault-tolerant systems simply by distributing workloads across multiple AWSs without needing to design their own data centers. 1. Independent power infrastructure. Each availability zone has its own power systems. Power is sourced from separate utility providers whenever possible. Electricity enters each AWS through different physical routes. Every AWS includes uninterruptible power supplies, UPS, and on-site diesel generators. So if there's a power outage affecting one AWS, the others continue running normally. Key takeaway: a power failure in one AWS does not cascade to other AWSs. 2. Independent networking and connectivity. AWSs also have isolated networking infrastructure. Each AWS has its own routers, switches, and network equipment. Network traffic travels through diverse fiber paths. Failures in one AWS's networking hardware do not impact others. Even though AWSs are connected by high-speed, private AWS links, those links are designed with redundancy and isolation in mind. Result: network failures stay contained within a single AWS. 3. Physical separation between AWSs. Availability zones are physically separated by miles, often between 10 and 60 miles apart. This distance is intentional. It protects against fires, floods, earthquakes, severe storms, localized infrastructure failures. By separating AWSs geographically, AWS prevents regional scale failures from starting with a single local incident. 4. Shared responsibility for logical isolation. Here's an important exam nuance. AWS guarantees physical isolation between availability zones. But customers are responsible for logical isolation. This means AWS ensures AWSs don't share power, networking, or facilities. Customers must deploy workloads across multiple AWSs. If you place everything, EC2 databases, load balancers, in a single AWS, you've created your own single point of failure, even though AWS gave you the tools to avoid it. Here's the mental model you should lock in. Regions provide geographic isolation. Availability zones are independent failure domains. AWSs do not share power, networking, or physical infrastructure. Multi-AWS deployments equals high availability and fault tolerance. If an exam question asks, how does AWS prevent single points of failure? The answer almost always comes back to availability zones and multi-AWS architecture. Once you truly understand this concept, a large number of cloud practitioner questions become straightforward. Describing when to use multiple AWS regions. Now let's talk about when and why you would use multiple AWS regions, because this is a key decision point in AWS architecture and a frequent exam topic. First, remember this foundation. AWS regions are completely isolated geographic areas. Each region has its own availability zones, infrastructure, and services, and AWS does not automatically share data between regions. Using multiple regions is not the default choice. It's something organizations do only when their business or technical requirements go beyond what a single region can provide. Let's walk through the main scenarios where multi-region architectures make sense. 1. Disaster recovery and business continuity. The most common reason to use multiple regions is disaster recovery. A multi-AWS architecture protects you from data center failures, but it cannot protect you from a full region outage, which could be caused by natural disasters, large-scale power failures, or major network disruptions. In a multi-region disaster recovery setup, one region runs production workloads. A second region acts as a disaster recovery location. Data is either backed up regularly, or continuously replicated to the secondary region. This approach supports aggressive recovery time objectives, RTO, and recovery point objectives, RPO, which are critical for mission-critical applications. AWS services commonly used here include Amazon S3, cross-region replication, Amazon RDS cross-region RED replicas, Amazon Route 53 failover routing, which automatically redirects traffic when the primary region becomes unhealthy. 2. Data sovereignty and compliance requirements. Another major driver for multi-region deployments is regulatory compliance. Many organizations are legally required to keep data within specific geographic boundaries. These rules may come from government regulations, industry standards, or contractual obligations. For example, European customer data may need to stay within the EU. Financial or healthcare data may be restricted to certain countries. In this case, organizations select AWS regions that align with those requirements, such as EU Central 1, Frankfurt, EU West 1, Ireland. AWS supports this by keeping data within the chosen region unless explicitly moved, providing compliance documentation through AWS Artifact. This allows customers to meet data residency and audit requirements without managing their own physical infrastructure. 3. Low latency for global users. Multi-region architectures are also used to improve performance for global users. If your application serves users across multiple continents, hosting everything in a single region can lead to high latency for distant users. To solve this, organizations deploy full application stacks in multiple regions. Users are routed to the nearest region. This dramatically improves page load times, API responsiveness, overall user experience. AWS services that support this pattern include Amazon Route 53 geolocation or latency-based routing, AWS Global Accelerator, which optimizes network paths across AWS's global backbone. 4. Business continuity and operational independence. Finally, some organizations use multiple regions to reduce business risk. Running in more than one region protects against regional connectivity failures, large-scale geopolitical disruptions, widespread utility outages. In these cases, organizations want operational independence so that problems in one region do not completely stop the business. This is common in financial services, global SaaS platforms, critical infrastructure systems. Putting it all together, exam summary. Here's how to think about this for the exam. You use multiple regions when you need disaster recovery from full region outages. Think Route 53 failover, S3 CRR, RDS cross-region replicas. Data sovereignty and compliance. Think choose regions that align with legal requirements. Low latency for global users. Think Route 53 routing, global accelerator. Higher business resilience. Think reduced dependency on a single geographic area. One final reminder. Multi-region architectures increase cost and complexity, so AWS customers only use them when the business justification is clear. That trade-off, resilience versus complexity, is exactly what AWS expects you to understand for the Cloud Practitioner exam.